Hello everyone, I'm Manu and today I'm going to talk to you about origami-inspired morphing. Folding is a key process at the heart of morphing and transformations that occurs in nature. From the formation of proteins to vast mountain ranges, it's evident across the length scales. Sentient structures that incorporate sensory functions as well as proportionate mechanical response are tutored to be the systems for future. And Origami Principles offers an elegant yet simple transformation path for a 2D substrate to morph into functional 3D form. In synthetic smart system, morphing is mainly realized by means of a strain mismatch. And there are different ways to realize this differential in a substrate. As we shall see from the examples, a common approach is to use shape memory alloys or polymers in a composite fashion to define hinge regions. These shape memory materials requires a programming step where they are stretched at elevated temperatures followed by cooling with the strain on. Heating of the material above its glass transition temperature releases the internal locked-in strain, driving the transformation. Another simple but comparable approach is to pattern hinge regions with blacking, facilitating localized heating above glass transition temperatures. These materials can also be integrated into the domain of 3D printers, and the shapes created can actuate in time domain, and this is termed as 4D printing. And state-of-the-art 3D printers now allows digital mixing of material to assign different TG glass transition temperature to the hinge regions so as to allow sequential actuation of a form. Hydrogels represents another class of material which is of interest with regard to morphing. Strain mismatch here can be realized by means of a rigid phase. This could be local cross-link points, or it could be another material, or through the use of short fibers within a swellable matrix to control the strain mismatch. These examples demonstrate morphing, but they do require complex programming and manufacturing steps or involve sophisticated chemistry. Here, we present a methodology to realize folds and curves in fibrous substrates such as paper without the complexity in terms of material, fabrication, and chemistry involved. We pattern fold lines on paper with a specific formulation of hydrogel, and the drying results in morphing, which can be maximized by drying at an elevated temperature. Shrinking of hydrogel due to water loss results in strain mismatch, which drives these forms. It's a diffusion-dominant drying mechanism assisted by capillary forces and surface tension of the gel. The fold angle is shown to be dependent on the amount of gel-forming polymer, its spread, and obviously stiffness of the paper and the area that needs to be folded. Drying at room temperature only removes the free water within the hydrogel. However, drying at elevated temperature removes the bound water from the gel, resulting in greater shrinkage, maximizing the morphing behavior. The temperature chosen here will also result in self-cross-linking points within the hydrogel, and this is crucial for repeatable actuation of these forms. Shown here are some common origami shapes realized with this method. We have spiral with different chiral parameters and flat annulus, which is morphed into a saddle-like shape. This methodology is not limited to curves and fold. Shown on the left is the independent response of gel drying on paper, but it can be antagonistically coupled to create pop-up shapes from a 2D substrate. These are quite resilient as they can support masses much greater than them. The curves are locked in place and they do not collapse even after opening them up. The polymer used to form gel is carboxymethyl cellulose, which is commonly used in food and skincare industry. Due to the nature of manual extrusion and inherent variability within paper, the standard deviation between samples are rather high at this stage for in-depth characterization. This can be mitigated by adopting a controlled dispensing system for the hydrogel and also integrating cellulose to the landscape of additive manufacturing methods to enable 4D printing of this material. This methodology and materials used here shows promise, and with further development, we can achieve simple, cost-effective smart material systems with low ecological footprint. Thank you.